A ladder-type graph has two n nodes and is represented as in the figure. If n equals 11, in how many ways can we choose n of the graph's edges such that no two of them share a common endpoint? Solving it for n equals 11, quite the number, huh? Well, I always like starting with smaller examples. So let's do just that. Let's take n equals 1. We need to choose just one edge. There's only one way to do that, just connect the first vertical pair of nodes. Simple enough. Now, what about n equals 2? We need to choose two edges, making sure no two share a common endpoint. There are two valid options, connect x1 with y1 and x2 with y2, the two vertical edges, or connect x1 with x2 and y1 with y2, the two horizontal edges. So, we have two ways to do it. Let's recap. N equals 1, we have one way. N equals 2, we have two ways. Now, back to the general case. Let's think about how we can break the problem down. Suppose we first choose the vertical edge between x1 and y1. We've now used those two nodes, and we're left with n-1 pairs to process. That's the same problem, just with n-1 instead of n. Alternatively, we might start by connecting x1 with x2 and y1 with y2. Now we've used 4 nodes, so we're left with n-2 pairs. Again, the same structure, just smaller. So what's happening here? Every time, we split the problem into two smaller problems, one where we remove one pair of nodes, the vertical case, one where we remove two pairs, the horizontal case. It's a classic case of divide et impera, divide and conquer. This naturally leads to a recursive pattern. To solve for n, we just add the number of solutions for n-1 and n-2. Sound familiar? Yep, it's the Fibonacci sequence. So for n equals 3, it's 1 plus 2 is equal to 3. For n equals 4, it's 2 plus 3 is equal to 5, then 8, 13, 21, and so on. So, the final answer is 144 ways to choose n equals 11 edges such that no two share a node.